In section 11.5, we're going to learn about compound probability problems that contain the words or and without constructing tree diagrams. So when we talk about an or probability problem, we require a successful outcome for at least one of the events. So for instance, suppose we draw one card from a deck of 52. What's the probability that we get an ace or a spade? So in this case, a success would be getting an ace or a spade. So let's consider a Venn diagram where we think about how we're going to calculate this probability. So this goes back to our section on sets that we studied earlier in the semester. So if you look at the Venn diagram here, you notice there's two sets in it. And if we look at this as all the events that are in outcome A and all the events in outcome B, then the probability of A or B is going to be the probability of event A plus the probability of event B. But we notice that the intersection right here is included in A and also in B. So we have to subtract the probability of A and B, or we're not going to get the right answer. Now, if the two events, and we call this an addition formula, sometimes it's called the general addition formula. Now, if the events are mutually exclusive, which means, for instance, the one that we talked about up here, getting an ace or a spade, there is no card in the deck that's an ace. Oh, I'm sorry, there is one. If we said getting an ace or a 10, those two items or events cannot happen at the same time. So it would look like this. And here we would just add the two probabilities together when the events are mutually exclusive or disjoint. Now when we have and problems, here we want to find the probability of the first event and also the second event. And so we're going to use this formula, the probability of A times the probability of B. And when we do this, we want to always assume when we're calculating the probability of A, we're going to assume that probability of B, that event A has already occurred. And in the next section, next week, when we talk about conditional probabilities, we'll have a more formal definition of that. So independent events, two events are independent when the probability of the occurrence of either event in no way affects the probability of the other event. And if the occurrence of either event has an effect on the probability of the other, we say the events are considered to be dependent. So let's work some problems from this section. So in the first problem, we're simply going to, first two problems actually, we're simply going to be applying the definition of the addition formula. And let's go ahead and write it up here. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And some people like to remember that when you have an or problem, you're working with an addition formula. So notice here, there's four quantities. So if I give you three quantities, you can calculate the fourth quantity. So here we want to find the left-hand side, the probability of A or B, and they've given me all the other probabilities. So we want to calculate the probability of A or B, and it's equal to the probability of A, which was given to me as 0.6, plus the probability of B, which is also given to me as 0.6, minus the probability that both occur. And then we can go ahead and simplify that. 0.6 plus 0.6 minus 0.3 gives me 0.9. So in this case, the probability of event A or B occurring is 0.9. Yeah, let's do another one. This time we want to find the probability of A and B, and we're given the other probabilities. So we were given the probability of A or B, the left side, 0.7 is equal to the probability of A plus the probability of B minus, and this is what we want to calculate, the probability of A and B. All right, so how can we do that? So first thing we want to do is we want to add together the 0.6 plus the 0.3, and we'll get 0.9. Now, there's two ways we could simplify this. I think the best way to do it is to go ahead and move the 0.7 over to the right side. I'm going to bring this up here so I have enough space. So on the left-hand side rather, now I have a 0, and I have 0 equals 0.2 minus the probability of A and B. But this is one I want to solve for, so I'm going to go ahead and add that to both sides. And so my answer I get is the probability of A and B both occurring at the same time in this problem is 0.2, and I can check that. So if I take 0.6 plus 0.3 is 0.9, subtract the 0.2, I get back to the probability of A or B, which was 0.7. All right, so let's work some application problems now. And we're going to be working with a card deck, and we're going to draw one card from the card deck, and we want to know the probability that we get an ace or a 7. So if we notice, here's my aces, and here's my sevens right here, and we notice those are disjoint. So the probability of an ace or a seven, I can simply add together the probability I get an ace plus the probability that I get a seven. Okay, so how many aces are in the deck? 4. Remember, there's 52 cards in that poker deck. And how many, what are we doing, sevens? There's also 4. So we have 8 out of 52. And if we divide that numerator and denominator by 4, we get 2 out of 13. All right, let's do another one from a card deck. This time we're going to do events that are not disjoint. We want to calculate the probability of a red card or a queen. And those are not disjoint because we have red queens. So we're going to calculate it like this. The probability of red or queen is the probability of red plus the probability of queen minus the probability of red and queen. All right, so how many red cards do we have in the deck? So we know half of them are red. And I'm going to keep this as 26 over 52. I'm not going to make it 1/2 for right now. And how many queens? We know there are 4 out of 52. And then how many red queens are there? There's going to be 2, queen of hearts and a queen of diamonds. So I have to subtract 2 over 52. So I have 26 plus 4 is 30 minus 2, 28 over 52. And I can divide by 4, so 7 over 13. Okay, let's do a problem now with a die. So when I roll a die, I know my outcomes are 1, 2, 3, 4, 5, and 6. And we want to calculate the probability that we roll a 3 or a 6. And so we know those are disjoint, so we can just do this as the probability of 3 plus the probability of 6, and each of those is 1/6. So we get 2 over 6 or 1/3. Okay, now let's change a little bit. This time the events are not disjoint. We want to roll an even number or a number less than 3. So probability even or less than 3. So that's going to be the probability of an even number plus the probability the number is less than 3 minus the probability that it's even and less than 3. Okay. So out of those 6 rolls, out of those 6, how many are even? 3 of them, right? Okay, how many are less than 3? There's 2, right? So that's 2 out of 6. And then we want to subtract even and less than 3, and there's going to be 1, which is the 2. So we have 3 plus 2 is 5, minus 1 is 4. Oops, 4 over 6 simplifies to 2 over 3. Okay, so we did dice, we did card deck, and now we're going to do one a little bit different this time. So we have some colored envelopes, and I'm going to write the colors here in case anybody has trouble seeing them. So we've got 3 red, 2 blue, 1 green, and 1 yellow envelope. We're going to pick one at random, and we want to calculate the probability that we get yellow or blue. Yellow or blue. And so yellow, we notice there's 1, so that's 1 out of, and we need the total number here, and there's 7. And blue, and there's 2 blues. So this is simply 3 out of 7. Now we're going to pick one, and we want the probability that we get an envelope other than red. So probability not red. So out of those 7 envelopes, how many are not red? We see 4. Now we're going to pick 2 envelopes with replacement, and we want to determine the probability that we get not red and, oops, I should have put an R there, not red. So not red and not red. So the first time we go in to pick how many are not red, we know its probability is 4 out of 7. We're going to put that envelope back, and we're going to pick again, so it's going to be 4 out of 7 again. So 16 out of 49, and that was with the replacement. Okay, now we're going to pick 2 envelopes, and we want to determine that they're both red. So probability red and red. And we're sampling with replacement. Okay, so the first time I go in, how many red envelopes do I have? I have 3. Okay, I'm going to put that envelope back, and I'm going to pick again, and I still have 3 to pick from. So it's 9 over 49 for my answer there. Okay, now If two are randomly selected with replacement, determine the probability at least one is red. So probability at least one of two is red. And if you remember, we went over this in the last section. And how do we do that? We use the complementary event, 1 minus the probability of no red. And we just did that, didn't we? Because we did no red and no red up here for 2. So it's going to be 1 minus 16 over 49, which comes out to be 33 over 49. Remember, when you're doing an at least probability, you're generally going to do it as 1 minus the complement, which is none of those events. And then finally, if 2 are selected with replacement, determine the probability that the first is blue. So probability of blue, and then yellow. Okay, so this time, first time I go in to pick, there are 7 envelopes. There's 2 blue. I'm going to put that first envelope back. Now, notice it doesn't matter what happened the first time. I still have 1 yellow on the second draw out of 7. So I've got 2 out of 49 for that probability. All right, let's do another one. This time we're going to have sentences to work with. So this time we're having a survey of senior citizens at a doctor's office. And it shows that 49% take blood pressure medication, 40% take cholesterol medication, and 1% take both. What's the probability that a senior citizen takes either blood pressure lowering or cholesterol lowering medication? So we want to calculate the probability of blood pressure or cholesterol. I'm going to abbreviate it like that. So it's going to be the probability of blood pressure medicine plus the probability that they take cholesterol minus, and remember, some of them are taking both, so we have to subtract the probability that they take both. Okay, so if we look at one senior citizen, what's the probability they take blood pressure? 0.59. And the probability they take cholesterol is 0.4. And then the probability that they take both is given as 0.01. And so if we go ahead and simplify that, we get 0.98. So almost all of them are taking at least one of those medications. Okay, now we have an IRS auditor selecting 3 tax returns. Notice this time without replacement from 55 returns, of which 10 have errors. What's the probability that she selects none of those with an error? Okay, so first question is, how many have no errors? So no errors means how many of those? So there's 55 total, 10 have errors, so we know 45 must have no error. So probability of no error on 3. Let's write it like that. Okay, so the first time I go in to pick, I have 55 to pick from, and I just said 45 of those don't have an error. Now we're going to sample without replacement. So we're not going to put that first one back in, so we have 54 left. And we're going to assume the first one didn't have an error, so we have 44 left to pick from. And then likewise on the third draw, we have 53 left to pick from, and 43 of those don't have an error. And if you go ahead and multiply that all out, let me jump through my pages here, it comes out to be 0.59, I'm sorry, 5409 if you simplify that. Okay, now we're going to do one with Scott and his baseball. So he has a bucket with baseballs. It has 18 Diamond, 14 Rawlings, and 4 Wilson. Scott's randomly selecting 2, and we want to determine these probabilities. And we're going to do this with replacement and then without replacement. Okay, so first thing is, how many baseballs does he have? 18 plus 14 plus 4, so there's 36 balls altogether to pick from. Okay, so first thing we want to do is probability that we pick a diamond ball and then a Wilson. And we're doing this with replacement. So first time we go in, we have 36 balls to pick from. How many are diamonds? 18. And then the second time we go in, we're going to pick, again, we're going to put the first one back in. So we still have 36. And we have Wilson on the second draw, so there's 4 there. Okay, so we want to simplify this. You notice 18 over 36 is 1/2. 4 over 36 is 1 over 9. So this comes out to be 1 over 18. Now we're going to do the same thing, but we're going to do it without replacement. So Diamond and Wilson. Okay, so the first one's going to be the same, 18 over 36. But now when we go back, we only have 35 balls to pick from. Now, it doesn't matter that we picked a diamond the first time, because the second time we want to pick a Wilson. And how many Wilsons are there? There's still all 4 remaining in there. So let's see what we can do to simplify here. We have 1/2, and then we still have the 4/35. And then I can divide 2 into here, so I end up with 2/35. So slightly different. If you get the decimals on here, they're a little tiny bit different. So sampling without replacement and with replacement yield slightly different probabilities. All right. Let's do one more scenario. So this time you've got the information in a little table. We have a sample of 30 people. There's the total. Who were recently hired an attorney were asked if they would recommend their attorney to a friend. So we want to calculate some probabilities here, and we're going to pick 3 people. And you're going to assume in this case you're sampling without replacement. So we want to calculate the probability that all 3 recommend. All right, so the first time we go in to pick, we have 30 people to pick from. And how many would recommend? 23. Now we're going to go back in. We're not going to replace the first person. So we have 29 people left. We're going to assume the first one would recommend. So this drops down to 22. And then again down to 28 on the third draw and 21 there. And if you go through and simplify those, you should get, let's see if I can find my probability sheet where I work these all out. You multiply that all out, you'll get 0.4362. I'll let you check my arithmetic on that one. All right, now we're going to change it up a little bit. We're still going to pick 3, but we're going to have the probability the first would not recommend. So not, I'm going to call that NR, not recommend, but the second and third, and then recommend and recommend. Let's abbreviate it like that. Okay, so the first time we go in, we have 30 people. And how many of those would not recommend? 3. All right, so on the second draw, we have 29 people left. All the people who would recommend are still there. So this is 23. And then on the third draw, we have 28 people to choose from, and we've already picked one of the ones that would recommend. So the numerator here drops down to 22. And if you go through and multiply that all out, you should get 0.6233. All right, let's change it around again. Now we have the first 2 would not recommend, but the third one is not sure. So not recommend, and I'm going to abbreviate it that way, not sure. All right, so on the first draw, the 30 people, how many would not recommend? 3. All right, I'm going to take that person aside. So we have 29 people to pick from on the second draw. And we're going to assume we got one of the people who wouldn't recommend the first time. So this is going to drop down to 2. And on the third draw, we have 28 people, and all the not sures are still there, and there's 4 of those. So we have 4 out of 28. And if you go through and multiply that one all out, you get 0.000099. Okay, one more. Probability the first would recommend, and the second and third would not. So probability recommend, and then not recommend, not recommend. Okay, so on the first draw, recommend, you remember there were 23 people that would recommend, so this is 23 out of 30. Second time we go back in, there's 29 people left to pick from, and not recommend would be 3. So we can see this. This is 3. Okay, we're going to assume we got one of those people that wouldn't recommend, so this goes down to 2. And if you multiply this out, you should come out with 0.00567. So also pretty small, but not quite as small as the one before. So that's the material from 11.5.